Great. Welcome, everyone. Thanks for joining the Pangeo Showcase today. We're really excited to have Henrique with us today. Henrique is a senior software engineer building systems at the intersection of large-scale data management and machine learning. Henrique is a core maintainer of Dask, focusing on its distributed computing engine. And Henrique is currently at Coiled, where he makes scaling Python computation in the cloud effortless. So yeah, we're really excited to have Henrique here with us today. And so Henrique, take it away whenever you're ready.
Yeah, thanks for the introduction. I'll just share my screen and get started. So yeah, today I want to talk with you about Dask Array and how it's scaling up to terabyte level performance. What will I roughly be talking about? I won't be giving you an intro to what Dask Array is. I hope people who showed up are familiar with that. I'm more interested in talking to you about some of the improvements that we've made recently in Dask Array that are also connected with Xarray and how they make workloads that were previously either very annoying to run or purely impossible to run work like a charm, basically. So yeah, a few words about myself here. As I mentioned already, I'm a senior engineer at Coiled. My background is in computer science, mostly on building actual scalable data systems. And I work at Coiled both on Dask as an open source product, focusing on the distributed engine and data shuffling in particular. But I also work on the cloud platform that Coiled offers. So for people who don't know Coiled, I'll give you the 10-second rundown as the only marketing in place here. Coiled is a platform that makes it easy for people to scale their computations, their Python computations to the cloud. So basically, you can take whatever you ran on your machine, whether that is something like Xarray and you want to scale that to thousands of VMs on AWS or GCP, for example, or that is just something where you need a very, very large notebook or maybe one machine with a GPU. We make that very easy for you. So let's first, for those who don't know what Dask is, this is the one slide that I have prepared for you here. What Dask does is that it serves as a backend behind the scenes, behind your Xarray computations, that lets you scale out your computations. So the way this works is, as usual, you just write your Xarray computation graph, and then as soon as you want to fetch your results, Xarray actually hands over work to Dask. Dask creates a big graph of individual computations that need to run, send them off to some cluster that you have spun up on, well, whatever really, whether that's AWS, it's your university's HPC Slurm cluster, or something like Coiled. And then it can use all of those machines to run distributed computations with much more cores available than you'd usually have, and also, of course, much more memory power. And this way, it helps you to really scale your computations beyond what your local computer could offer. Why am I talking about improvements to Dask Array now? I've seen that the community had a bunch of problems with Dask Array for a while now, and development has sort of been flat. So why did we, as Dask developers, end up picking this? Well, one thing is, at Coiled, we employ a bunch of Dask maintainers, and what we saw was that people were coming in with geospatial workloads, and they just had problems scaling them. We took a look at the code that they ran, and then we just figured that, well, knowing what we know about Dask, there are actually a few pretty simple improvements that we can make to how Xarray computes stuff here. to give you a bunch of quick wins. Now, since we saw that a bunch of our customers had problems, we figured, well, probably more people are running into problems. So what we did was that we solicited a bunch of geospatial benchmarks from the wider Pangeo community. So you might have seen this issue on Pangeo discourse, where a colleague of mine, James, solicited a bunch of workloads that people care about and that might not be running very smoothly. We got some feedback from folks, and we implemented a few different workloads covering different kinds of things that you like to do in geospatial analyses. And what we happened to see was, for one, there's a large overlap between the problems that customers had and that the general community had. So this is nice. This makes it easy for us as people who have to build things that solve business problems to verify, well, we're spending money on things that help everybody. And the other thing that we saw was a lot of people were building code that looked very awkward to us, but that essentially was just working around loads of problems that people were facing within Dask. And we thought that, well, this can't be the best thing that we can do here. People shouldn't fight Dask. Dask should make it easy for them to run the computations. And so with that, we essentially went to work. So I can't cover all the improvements that we made in the recent past. I want to focus on two particular problems. One is rechunking. I think most people here know what rechunking is, but basically the pathological case is, imagine you have a data set, you have sensor measurements for some area, maybe the entire world, one per day. So your data is chunked that way, of like one file lying around for each individual day. But now if you want to do a computation like a median over time, what you need instead is that each chunk that you're processing, each chunk that you're handing to one VM, has to include all the points over all time for this one specific geographical location. So basically what they're saying is each of these inputs here is part of each of these outputs. And that's just nasty. The way that we moved data around in Dask previously was using task-based shuffling, but that had the main problem that we created a lot of very small intermediate tasks, and each of those tiny tasks creates a lot of overhead. It creates overhead on the scheduler because it has to hold them in memory. It has to schedule them. This just didn't scale nicely. What we did instead is we built out a dedicated system for shuffling in Dask. And this system actually does all the data transfer under the hood. It hides it from Dask's general task-based internals, and it just uses them for coordination and consistency. And the effect that this has is that we don't see this blow up in tasks. Instead, each of the inputs just feeds into one barrier task, and the barrier task feeds into each of those outputs. Everything else is hidden from this system. The effect that this has is, well, the number of tasks is reduced dramatically. So if people have done some complexity theory, it reduces things from n log n to just O of n. So basically now things just scale linearly with the number of input chunks that you have. And also, even more importantly, data, because it's hidden now in this dedicated subsystem, is very explicitly moved between memory and disk. Task-based shuffling relied on Dask's billing mechanism to move data onto disk if it sees workers running out of memory. Sometimes it was too slow, so workers did actually run out of memory. Now we don't have that problem anymore. to give folks a demo, I thought it would be a nice idea to just show you how fast we can shuffle data or rechunk data on a 1 TB data set from era 5. Problem is, if we use task-based rechunking, that just didn't work. We see here is memory footprint of a scheduler that I chose to just execute this, and it ran out of memory, and I gave it way more memory than I usually would have. So it has 64 gigabytes. That should be plenty to just do one rechunking operation. Well, to give you still some comparison, let's scale it down a bit. As we saw that task-based rechunking doesn't play nice with large numbers. And let's see how that goes. For this, I've created a small recording here because it allows me to skip between things. And here we just saw that I submitted some tasks. It'll take about a minute for them to arrive on the cluster. And on the right side, we see P2P shuffling and P2P rechunking. We saw that because the number of tasks is smaller, this has already kicked off faster than task-based shuffling and rechunking does. And now we see also that here we have around 56,000 tasks, and here we have 150,000 tasks. So we already see the difference in total number of tasks. This just grows larger, this difference, if we scale up the data set. And now if we skip a bit ahead, what we see is task-based shuffling builds up more and more memory over here. Yellow workers are the ones that have to start moving memory to disk in this spilling mechanism, which has its quirks. Over here, we see that memory usage is just staying flat. So this system does a good job keeping the overall memory footprint low, which also makes this much more scalable because it doesn't run into potential problems of a worker, just dying because it cannot allocate any memory anymore. This will continue for a bit. I won't run the entire thing. Basically, what we see in the end, P2P is even faster than task-based shuffling. So it's not just more scalable, it's actually also faster. Now, P2P, as I showed you, is great in these all-to-all like situations. But task-based rechunking has its big advantage in situations where you just rechunk neighbors only. So imagine you have a data set where things are more or less aligned by a month, but you actually need to have strict month boundaries. So in every case, you need to join 2, maybe 3 chunks, one at a time, never the whole data set with the whole data set, essentially. So because of that, we can't just say always use P2P. Instead, what we did is in Dask from August last year, starting from there, we have automatic selection of the rechunking method in there. I hope most people have started playing with this at this point. If not, I encourage you to do so. We hope that we got the heuristics right. If not, please let us know. So much for rechunking. The other thing I want to talk with you about is downscaling workload. This is something that we saw both in climatology computations, but also in our customer computations. And basically, what we did in a very simple form of this is we have a few rolling means. And we need to calculate that on, say, in this case, 26 gigabytes of data. That shouldn't be all too hard, right? Well, if we just do this, we suddenly get a warning that we multiply our number of tasks by 31. That's kind of bad. And it also complains that things are running out of order. Well, if things are out of order, maybe we should just try sorting stuff. This is actually a much worse idea than what we had before, because now it's not a 31x increase, it's a 365x increase. The effect that this had is that we started off with roughly 190 chunks. We ended up with almost 70,000 of them. And this means that every simple operation, just multiplying the data set by 2, would just create an additional 70,000, 67,000 tasks. And this just doesn't scale well. Well, so what we did is we actually went back to the drawing board and re-implemented the entire algorithm here. And afterward, what you can see is, yeah, the number of chunks stays roughly the same. Also, chunk sizing, I haven't shown you this before, stays roughly the same. So this is 150 megs. This is 72 megabytes. Before, this was suddenly down to 405 kilobytes. As a general rule of thumb, anything between like 50 and 250 megabytes is probably a good value. You should not drop below 10 megs. So this is much better than before. But it doesn't stop there. What happens if we actually just want to calculate a median instead of the mean? Well, we kind of know this plot. So this computation, once again, it just doesn't work. In this case, it tried to construct the graph on a client machine. And even though we gave it like 130 gigabytes of memory, it still didn't cut it. And this entire process took an hour. So there was a complete failure. One problem in here was that we suddenly saw a huge increase in the amount of data because of how rolling construct works, which we need to use under the hood. So our 25 gigabytes actually became something like 22 terabytes. And we saw a whole new host of different problems. I won't go into details on all of them, but basically, apart from the problems that we saw before, we also had problems that rolling construct created terabyte-sized chunks. Good luck trying to fit a terabyte of data into memory on your average cloud machine. Graph construction just took dozens of minutes for some of the underlying operations. That also doesn't scale well. And medians and quantiles, using NumPy, which did under the hood, we're just locking up the GIL. We're completely freezing up worker processes. So none of this actually worked. And what we saw was once we chipped away at the individual problems, things started working nicely, but only once all the problems were fixed. So what's my conclusion for you here? Dask Array used to be pretty meh. Like if you wanted to scale to a lot of data, it didn't really do that well for you, but it's become a lot better now. Dask Array has also become a lot simpler and more scalable across many different workloads. We've tried to make chunking much more sane so that you don't end up with way too many or way too few chunks. And the most important bit is that these problems have highlighted that we as Dask maintainers are pretty good at fixing those problems, but we're not good at knowing these problems. So we really rely on you as domain experts on highlighting whatever performance or scalability problems are if you use Dask as a backend for Xarray, and just complain when something seems like it should not take as much time or as much memory. And more importantly, if the code you have to write for this looks very weird and complicated, it probably also shouldn't do that. Like it should look very easy. And with that, all I can say now is kudos to Patrick and Deepak, who did most of the actual work on these things. And yeah, love to hear questions and discuss things.